Welcome to cosmic sedation, a place where stars hum and galaxies softly breathe. Tonight's topic: what if the cosmos is a living thing? As we drift into this quiet night, subscribe for more cosmic comfort, and like if you're ready to explore the universe's gentle rhythm with us. Drop a comment letting me know where you are tonight and what time you usually fall asleep. We are just beginning our journey through the stars. Let's ease into it together. Despite the relentless march towards darkness, every dying star broadcasts light brighter than its birth. In deep space, temperatures can plummet to -270 degrees Celsius in vast molecular clouds, mere fractions above absolute zero. Yet, paradoxically, a single supernova can outshine entire galaxies with blinding brilliance as it collapses into nothingness. This dance of extremes, icy cold and scorching heat, is the heartbeat of the cosmos. In our own Milky Way, new stars coalesce from clouds of molecular hydrogen that span hundreds of light years. These nascent stars gather mass through gravitational attraction, gradually compressing until nuclear fusion ignites in their cores. Consider a star like Betelgeuse, which is now nearing the end of its life cycle. It has swollen into a red supergiant, expelling vast amounts of matter into space with each stellar wind. These ejections provide the raw materials for future stars and planets to form. Our Sun, by contrast, is still in its main sequence phase, having shone steadily for nearly 5 billion years, and set to continue doing so for another 5 before it eventually becomes a red giant and then a white dwarf. Every star that lives and dies contributes particles to the interstellar medium, which eventually seed new generations of stars. This recycling ensures a continuous cycle of birth and rebirth. The universe is teeming with processes vital for our existence. The iron in your blood was forged in a star that died before our Sun even formed. These elements are now part of you because of cosmic cycles dating back billions of years. Each supernova disperses heavy elements throughout the galaxy, enriching its fabric. Without these explosions, Earth itself would not be possible. As stars die and scatter their contents into space, they set the stage for future stellar nurseries. The universe is perpetually recycling matter on a scale that defies human comprehension. A single supermassive black hole at the center of our galaxy contains as much mass as 4 million suns. Its gravity pulls in material from surrounding regions, causing it to accrete and heat up. This process can influence star formation by compressing nearby clouds. Yet, despite its massive presence, this black hole is only one of many cosmic entities engaged in an ongoing dance of energy transfer throughout the cosmos. The Andromeda Galaxy, moving towards us at a speed of about 110 kilometers per second, will collide with our Milky Way in approximately 4.5 billion years, further illustrating the dynamic nature of stellar interactions on a galactic scale. The cosmic microwave background radiation, a remnant from the Big Bang, has an average temperature of about 2.725 Kelvin. It permeates every corner of the universe, providing a snapshot of what our cosmos was like when it was just 380,000 years old. This radiation is so uniform that any deviation in its temperature could hint at the presence of cosmic structures or events from the early universe. Yet these minute fluctuations are minuscule, on the order of 10,000th of a degree Celsius. Such subtleties are crucial for understanding how galaxies and clusters formed over billions of years. In this continuous cycle, every star's death is not just an end, but also a beginning. The remnants of a supernova can become a nebula rich with elements necessary for new stars to form. This process has been ongoing since the universe first began, creating the diverse array of celestial bodies we observe today. Each cycle ensures that the cosmos remains dynamic and evolving, constantly reshaping itself through birth and death on an unimaginable scale. The observable universe expands at a rate faster than the speed of light, a paradox that defies our understanding of space and time. This expansion stretches the fabric of space-time itself, pulling distant galaxies away from us with an inexorable force. Imagine a cosmic balloon inflating with tiny dots representing galaxies. As the balloon expands, these dots move farther apart without any physical movement in space. Only the distance between them increases. In 13.8 billion years, this expansion has stretched the universe to approximately 93 billion light-years across. For perspective, if our galaxy were a single grain of sand on Earth's surface, the observable universe would span from here to the Sun. This peculiar phenomenon is driven by dark energy, an invisible force that permeates all of space, pushing galaxies apart at accelerating speeds. On Earth, we experience expansion on scales too small for us to notice. Only in deep space does this effect become measurable. Near the event horizon of a black hole, gravity pulls objects inward faster than light can escape. Yet across cosmic distances, dark energy pulls space itself outward. The cosmic microwave background radiation provides evidence of the universe's rapid expansion just after the Big Bang. At an average temperature of 2.725 Kelvin, this faint echo from the early cosmos is nearly uniform in all directions, but contains minute temperature fluctuations that seeded the formation of galaxies. These variations are incredibly subtle, about 1 part in 100,000, and they hint at the intricate balance between expansion and gravitational collapse. In regions where space expands more rapidly, it can lead to peculiar phenomena such as voids, vast empty spaces with fewer stars than average cosmic density. One of these voids, known as the Boötes Void or Great Void, spans about 300 million light-years in diameter, making it one of the largest structures in our observable universe. Within this vast emptiness, galaxies are few and far between, creating a landscape that defies intuition. The expansion continues to accelerate, suggesting that distant parts of the universe will eventually become completely unobservable as they recede beyond the cosmic horizon, the point at which light from those regions can no longer reach us. In 4.5 billion years, when our galaxy merges with Andromeda, Earth's position in the expanding universe would have shifted slightly, but this local event pales in comparison to the ongoing expansion of space-time itself. The paradox remains. How can something grow faster than light without violating fundamental physics? Consider that for every second that passes, space itself stretches by a fraction of its size. Within these vast expanses, time behaves differently. For instance, as we look deeper into space, we are also looking further back in time. The light from the most distant galaxies takes billions of years to reach us, showing what they looked like when they were much younger. Yet, due to the acceleration of expansion, some parts of the universe are already unreachable, their light forever beyond our grasp. This phenomenon introduces a peculiar asymmetry. We can observe regions that are receding faster than the speed of light, because the light has had time to reach us from the moment when they were still within causal contact. The paradoxical nature of this expansion challenges our understanding of causality and locality in physics. It suggests that the universe is not just expanding, but doing so in a manner that defies our conventional notions of space and time. In contrast to the rapid expansion of spacetime, the local interactions we experience on Earth, like gravity binding objects together or light traveling through space, remain constant. A billion years ago, the Milky Way was a nascent galaxy, with stars still forming from vast clouds of molecular hydrogen. These clouds, some extending up to hundreds of light years in diameter, are where stellar life begins. The temperature within these clouds averaged around 10 degrees Kelvin, so cold that atoms barely move. Yet it is here that complex molecules, precursors to life, begin their journey through the cosmos. Today, our galaxy hosts an estimated 100 billion stars, each following its own gravitational path. At the galactic center lies a supermassive black hole with a mass equivalent to 4 million suns. This behemoth slowly draws in nearby matter, heating it to such extremes that it emits X-rays, radiation that would be lethal if encountered by human tissue. These emissions are not just random phenomena. They play a crucial role in regulating star formation and the overall structure of our galaxy. A billion years from now, the Milky Way will undergo dramatic changes. It is on a collision course with Andromeda, another spiral galaxy moving towards us at 110 kilometers per second. When these two galaxies merge, they will form an elliptical galaxy, a cosmic transformation that highlights the dynamic nature of galactic evolution. This merger will take billions of years to complete and will result in new stellar nurseries, as clouds of gas are compressed by the gravitational forces involved. The universe is not just composed of isolated galaxies. It is a web of interacting systems. Our Milky Way has ongoing interactions with smaller satellite galaxies like the Large and Small Magellanic Clouds. These encounters can trigger waves of star formation within both galaxies, creating ripples in stellar populations that echo through time. This interconnectedness underscores how events across vast distances are linked by gravitational forces, shaping the universe's structure. Throughout this cosmic cycle, our Sun has been a relative newcomer to the scene, having formed about halfway through the universe's 13.8 billion year history. The iron atoms in your blood were likely forged in ancient supernovae, explosions that release energy equivalent to trillions of nuclear bombs. These heavy elements are not only essential for life on Earth, but also tell a story of cosmic recycling, where stellar death and rebirth are intertwined. Consider the paradoxical nature of our existence within this vast structure. While galaxies evolve over billions of years, individual stars have much shorter lifespans. Our Sun, which has been shining for about 4.6 billion years, will eventually swell into a red giant before collapsing into a white dwarf, leaving behind its legacy in the form of these heavy elements. This cycle of birth and death plays out on cosmic scales far larger than our human experience can fully grasp. Yet it is this very process that makes life possible on planets like Earth. The universe's expansion not only stretches space, but also impacts the temperature of deep space. The cosmic microwave background radiation, remnants from the Big Bang, has cooled to an average temperature of 2.725 Kelvin. This near-absolute zero environment is so cold that particles barely have the energy to move. Yet within this frigid backdrop, stars continue their relentless cycle of formation and destruction, each contributing to the ongoing cosmic symphony. In contrast to the vastness of intergalactic space, consider the intimate connection between the cosmos and our own existence. The elements that make up your body were forged in distant stellar furnaces and scattered across the universe by supernova explosions. Each atom carries within it a history that stretches back billions of years, linking you directly to the stars themselves. This cosmic perspective reveals how the fate of galaxies is intertwined with the cycles of individual stars. As galaxies merge and evolve, they provide environments where new stars can form from the ashes of older ones. This cycle of rebirth ensures that elements essential for life continue to be created and distributed throughout the universe. In the vastness of intergalactic space, dark matter exerts a gravitational influence that molds entire galactic clusters into complex structures without emitting light or interacting with any known particles. This elusive force forms an invisible scaffold around galaxies, stretching across hundreds of thousands of light years. It is through the subtle distortions it causes in the paths of stars and galaxies that we can infer its presence. Each galaxy cluster moves within this vast web, shaped by dark matter's gravitational pull, which guides their collective motion. Imagine a sculptor working with invisible clay molding star systems into intricate patterns without ever touching them directly. This analogy captures the enigmatic nature of dark matter, whose influence is detectable only through its effects on visible matter. It constitutes about 85% of all mass in the universe, far outweighing ordinary matter like stars and planets. At the heart of galaxy clusters, where dark matter's gravitational pull peaks, it creates regions known as cosmic voids, vast areas devoid of galaxies. These voids are not true vacuums, but rather contain a diffuse amount of dark matter that is less dense than in galaxy clusters. The contrast between these dense and sparse regions underscores how the distribution of dark matter shapes the large-scale structure of the universe. The coldest place known to humans is not found within these cosmic voids. It lies within specialized laboratories on Earth, where temperatures can dip below 1/10,000,000th of a degree above absolute zero. This comparison highlights how conditions we perceive as extreme are often relative and context-dependent. Dark matter's influence remains just out of reach, an enigmatic force guiding the cosmos without ever interacting with light or particles. In billions of years, dark matter will continue to shape our universe. It will guide the eventual collision between the Milky Way and Andromeda, reshaping both galaxies into a new structure that could take millions more years to fully stabilize. For now, it remains an enigmatic force, silently shaping the cosmos without ever interacting with light or particles we know. Scientists use simulations and observations of galaxy movements to map out these invisible structures with remarkable precision. These maps reveal that dark matter forms intricate filaments connecting galaxies in vast cosmic webs, much like threads in a complex network. Yet, despite this detailed understanding, the substance itself remains as mysterious as ever, neither emitting nor absorbing any form of radiation. The role of dark matter extends beyond just shaping galactic clusters. It also plays a critical part in the formation and evolution of individual galaxies. Within each galaxy, dark matter provides the gravitational anchor necessary for stars to coalesce into stable systems. Without this unseen influence, many galaxies would disintegrate under their own velocity or expand uncontrollably. In some areas, dark matter concentrations are so high that they create what astronomers call dark matter halos. These massive structures can span millions of light years and contain more mass than all the stars within visible galaxies combined. The sheer scale of these halos is staggering, dwarfing even the largest known star clusters. Understanding dark matter not only deepens our comprehension of cosmic structure, but also challenges fundamental assumptions about physics. Its existence suggests that there are particles or fields yet to be discovered, potentially rewriting how we understand gravity and particle interactions on a universal scale. This enigmatic force remains a frontier for both theoretical physicists and observational astronomers alike. Despite its profound influence, dark matter does not interact with electromagnetic radiation in any measurable way. It is entirely invisible to telescopes that rely on light or radio waves to observe the cosmos. Yet, through meticulous analysis of gravitational effects, scientists can trace its presence across billions of years of cosmic history. This silent shaping force has been at work since the universe's earliest moments, guiding the formation of galaxies and clusters from the first microscopic density fluctuations in the primordial soup following the Big Bang. Dark matter's role in these formative epochs is crucial to understanding how structure emerged from chaos. Gravity's influence on time varies dramatically across different regions of space, creating profound disparities in how time is experienced. Near supermassive black holes, for instance, time dilates significantly due to the intense gravitational pull. An observer near such a singularity might witness only minutes pass, while millions of years elapse for someone at a greater distance. In contrast, consider Earth's orbit around the Sun. The Sun's gravitational field causes time to slow down slightly compared to deep space. As Earth moves through its elliptical path, it experiences minute variations in time due to these gravitational effects. This phenomenon was first noted by Johannes Kepler, but wasn't fully understood until Einstein's theory of general relativity. For astronauts on distant missions, the effects of time dilation become particularly pronounced. Months or even weeks might pass for them during transit, while years elapse back on Earth. These temporal distortions challenge our notions of identity and continuity. What does it mean to age differently from the rest of humanity? They also complicate communication between spacecraft and ground control teams, requiring sophisticated calculations to synchronize events across vast distances. Imagine a scenario where astronauts return home after a mission only to find their families have aged decades more than they have. Such discrepancies highlight the complex relationship between time, gravity, and human experience. Near supermassive black holes, time acts as a magnifying glass for cosmic evolution. Events that would take billions of years in other parts of space can be observed rapidly from such vantage points. In the vicinity of these singularities, extreme gravitational forces compress not just space, but also time itself, allowing observers to witness vast stretches of cosmic history unfold in mere moments. This capability provides unique insights into the universe's formation and evolution. In deep space, far removed from any significant gravitational influence or radiation sources, temperatures approach absolute zero. Here, atoms barely move due to the lack of thermal energy, making time nearly irrelevant at the atomic level. In stark contrast, near black holes, time is warped and cosmic events are accelerated, offering a different perspective on the universe's history. Reflecting on these phenomena, we recognize that the experience of time itself varies widely throughout space. From the rapid passage of time near a supermassive black hole to the almost frozen atomic motion in deep space, each environment offers unique insights into the nature of spacetime and its profound effects on cosmic processes. These variations highlight how gravity's influence can dramatically alter our perception of the universe, shaping both microscopic and macroscopic scales. Understanding these differences helps us appreciate the complexity of time across the cosmos. In regions far from any gravitational influence, such as vast intergalactic voids, time stretches out almost infinitely. These spaces are nearly empty, with only a few hydrogen atoms per cubic meter drifting through them. At temperatures close to absolute zero, just fractions of a degree above 0 Kelvin, the motion of these particles is virtually halted. In this environment, time itself seems to slow down, as if the universe has paused in its relentless march forward. For an observer in such a region, the passage of time would feel almost imperceptible. The lack of significant gravitational forces means that there's little variation in how time flows compared to more dynamic areas of space. However, this tranquility belies the vast scale of cosmic processes happening elsewhere. While minutes might seem long and uneventful, billions of years could be passing for distant galaxies as they drift through their own cycles of birth, life, and death. This stark contrast between the bustling activity near black holes and the serene stillness of intergalactic voids underscores the complexity of spacetime. In these quiet expanses, the universe appears to breathe slowly, with cosmic events unfolding at a pace that challenges our human perception of time. Yet, within this apparent stillness lies the potential for profound discoveries about the nature of reality itself. how gravity shapes not just space, but also the very fabric of time across the cosmos. In this silence, consider the paradox. While our ears perceive sound in terms of pressure waves through air or water, interstellar space lacks any medium to carry such waves. Yet this void is not silent merely because it's empty. Its silence speaks volumes about the vast distances and profound emptiness that characterize much of the universe. The absence of noise here does more than highlight isolation. It emphasizes the true nature of space itself, a place where particles are so sparse they barely interact. In some remote areas of deep space, the vacuum is so extreme that it approaches a state where even light experiences drag. This phenomenon, known as the dynamic Casimir effect, arises when boundaries move faster than the speed of light would allow in empty space. Here, the silence betrays a different reality, of a cosmos expanding into itself with no sound to mark its passage. The void between stars is not just an absence, but also a place where time stretches and slows down due to the universe's expansion. Between these isolated points of light, the silence remains unbroken. It serves as a reminder that while we are drawn to the brilliance of stars and galaxies, much of what defines our universe lies in its emptiness. The void between stars stretches for an average distance of about 3,000 light-years, an eternity of quiet where no sound can travel, not even the faintest thermal noise from cosmic microwave background radiation. This silence is a testament to the vast distances that separate celestial bodies in an ever-expanding cosmos. In contrast to the bustling activity of stars and galaxies, these regions between them are stark in their simplicity. They offer an opportunity for contemplation about scale and solitude. While stars burn brightly and supernovae explode with dazzling force, the spaces between them are defined by their emptiness and stillness. This is where the universe's story unfolds slowly, over timescales beyond human comprehension. The silence here is not just the lack of noise. It's a reminder of the immense distances that separate celestial bodies in an ever-expanding cosmos. This expansive quietude also highlights the cosmic timeline. From the Big Bang, which occurred about 13.8 billion years ago, to today's expanding universe. In these voids, time stretches out as space expands, creating conditions far removed from our everyday experiences on Earth. The temperature of 2.725 Kelvin in deep space is colder than anywhere found naturally on our planet, colder even than the coldest laboratory environments designed by humans. Here, atoms move at their slowest possible pace, a physical manifestation of near-zero energy. Finally, consider what lies ahead for these voids. As galaxies continue to drift apart due to cosmic expansion, their isolation will only grow. In billions more years, the light from distant stars may no longer reach us, and the night sky will appear increasingly sparse. Yet within this growing darkness, new molecular clouds will form, slowly condensing into future generations of stars. The silence in these voids is a precursor to the universe's eventual fate, where the expansion continues until galaxies are so far apart that their light can never connect again. In this vast emptiness, the universe's grand narrative quietly proceeds, guided by the laws of physics and gravity. This silent expanse also invites reflection on what it means to be a living thing in such an environment. Human bodies require molecules and particles for sound waves to travel. Yet, in interstellar space, there are no such mediums. The silence here is not just the absence of noise. It's a profound reminder of our reliance on physical conditions that exist only within specific environments, conditions far more abundant on Earth than in the vastness between stars. In some regions of deep space, temperatures approach absolute zero, where atomic motion essentially stops due to a lack of energy. This extreme cold is not found naturally anywhere on Earth and creates an environment so still it defies our everyday understanding of sound or even movement. These areas are among the coldest places in the known universe, colder than any laboratory can achieve artificially. The silence here is absolute, a place where even the faintest thermal radiation fades into nothingness. Consider also the role of molecular clouds within these voids. While vast expanses of space exist between galaxies and stars, pockets of molecular hydrogen span up to hundreds of light years, providing the raw material for future star formation. These clouds are the nurseries where new celestial bodies emerge, slowly coalescing under the influence of gravity. In contrast to the silence surrounding them, these regions hold the potential for life-giving processes that will shape the universe's future. The expansion of the universe continues to stretch space itself, pulling galaxies apart at an accelerating rate. As this happens, the voids between stars grow larger and more isolated. The cosmic microwave background radiation, a remnant from the Big Bang, provides a glimpse into the early universe's conditions. At 2.725 Kelvin, it is the only sound we can detect in these vast expanses, leftover energy from when the universe was much hotter and denser than it is today. In this context of expanding voids, consider how life on Earth perceives silence differently. On our planet, silence is often a rare moment between sounds, but in space, it is an unbroken continuum. The human ear evolved to detect vibrations carried by air molecules, yet in the vacuum of deep space, no such medium exists to carry sound waves. This profound. As you drift through an interstellar dust cloud, you find yourself in a region of space that feels both empty and full at the same time. The particles here are minuscule, some no larger than a micron across, and yet they carry within them the potential for stellar birth. These grains of dust have traveled vast distances, up to 100 light years, from supernovae or ancient molecular clouds. Each particle is a cosmic seed, drifting silently between galaxies. In this environment, temperature hovers just above absolute zero, about 3 degrees Kelvin, colder than the coldest known place on Earth, which is in Antarctica's East Antarctic Plateau. Despite their tiny size and sparse distribution, these dust clouds can span hundreds of light years, housing billions upon billions of such particles. If you were to touch one of these particles, an impossible scenario given the vacuum of space, your skin would experience a chill colder than any freezer on Earth could replicate. Yet despite this extreme cold, there is warmth here, albeit faint and ancient. The cosmic microwave background radiation, left over from when the universe was just 380,000 years old after the Big Bang. This radiation permeates every corner of space, its average temperature holding steady at 13.8 billion years after the event itself. Each particle you pass by is a relic of stellar death and rebirth, carrying within it elements that were once part of stars that died before our sun even existed. The iron in these particles was formed in supernovae explosions, while hydrogen and helium have been present since the universe's earliest moments. This cosmic recycling process ensures that every grain carries within it a history older than any star you might see from Earth. In some regions, these particles are clumped together more densely. These nascent formations could be the birthplaces of new stars or planetary systems. Gravity pulls at these clumps with increasing intensity, causing them to compress and heat up over time. In certain areas, you might encounter protostars forming, a precursor to full-fledged stardom. These nascent stars are still in their infancy, accreting material from the surrounding cloud. As they grow, they will eventually ignite nuclear fusion in their cores, becoming fully fledged stars. The process of star formation is a slow one, taking millions of years for these protostars to reach maturity. Nearby, you might also find regions where dust particles are more tightly packed. These could be the seeds of future planets and moons. In these dense areas, gravity pulls together more material than in other parts of the cloud, forming flattened structures around what will eventually become stars. The scale of this dust cloud is truly vast. It can span hundreds of light years in diameter, containing billions upon billions of particles. To put this into perspective, the distance from Earth to the nearest star, Proxima Centauri, is 4.2 light years. So you are floating through a space that could contain more than 20 such journeys between stars. Yet despite its vastness, it feels intimate. The individual particles carry their histories as they drift past you. Each particle carries within it elements that were once part of stars that died before our sun even existed. The iron in these particles was formed in supernovae explosions, while hydrogen and helium have been present since the universe's earliest moments. In some areas, you might encounter regions where the dust particles are clumped together more densely. These nascent formations could be the birthplaces of new stars or planetary systems. Gravity pulls at these clumps with increasing intensity, causing them to compress and heat up over time. These dense regions can span tens to hundreds of light years across, forming molecular clouds that will eventually give rise to stellar nurseries. Within these clouds, gravity works in a complex dance, pulling material together while also dispersing it through radiation pressure from nearby stars. This delicate balance is crucial for the formation of new celestial bodies. In some cases, however, this balance can be disrupted by passing stars or shockwaves from supernovae, leading to unexpected outcomes such as the creation of rogue planets or failed stars known as brown dwarfs. As you continue to drift through this cloud, you notice something unexpected, an area where the dust particles seem denser than usual. This region is likely a protoplanetary disk, the birthplace of new planets and moons. Here, gravity has pulled together more material than in other parts of the cloud, forming a flattened structure around what will eventually become a star. The process of planet formation is a delicate one, taking millions of years as dust and ice particles collide to form larger bodies. Eventually, these bodies grow large enough to clear their orbits, becoming full-fledged planets. In this region, you might encounter the early stages of this process, smaller bodies colliding and coalescing into larger structures. Nearby, in other parts of the cloud, similar processes are unfolding, each one unique. Cosmic inflation, a pivotal moment just after the Big Bang, saw space expand at an extraordinary rate, faster than light could travel. This phase lasted less than 1/1,000,000th of a second, but fundamentally shaped the universe we observe today. During this brief period, every point in space was stretched apart uniformly and exponentially. To grasp its scale, imagine placing a single grain of sand at each end of the observable universe, now spanning 93 billion light-years, and that initial distance would have been compressed into an infinitesimal speck within fractions of time. This rapid stretching laid down the foundation for the distribution of galaxies and cosmic structures we see today. Inflation caused spacetime to expand so dramatically that regions once in contact are now separated by distances billions of times greater than their original scale. Each point was stretched apart uniformly, leading to a remarkably smooth universe with only tiny quantum fluctuations, seeds for galaxy formation. These minute variations can still be observed through the cosmic microwave background radiation, an echo from 13.8 billion years ago at 2.725 Kelvin. Remarkably, this process did not violate Einstein's theory of relativity because it occurred within spacetime itself rather than through it. The stretching was so fast that no information could travel faster than light in the usual sense. This paradoxical behavior is a cornerstone of understanding how our universe formed and why distant galaxies move away from us at such incredible speeds today. The uniformity of the cosmic microwave background radiation provides strong evidence for inflation, as it demonstrates an incredibly even distribution of energy across the observable universe. Without this rapid expansion, variations in temperature and density might have been too extreme for stars and galaxies to form as we know them. Instead, these tiny fluctuations grew into vast clusters and superclusters of galaxies. Even now, long after inflation ended, its effects are still felt. For instance, the rate at which galaxies move away from each other is a direct consequence of this early stretching of space. The universe continues to expand today, though not as rapidly as during inflation, ensuring that distant galaxies will eventually become too far apart for light from one to reach another, forever isolating them in an expanding cosmos. In billions of years, our own Milky Way galaxy will collide with Andromeda, illustrating the local dynamics of cosmic structures, while the vast expanses beyond remain forever out of reach. The process of cosmic inflation also explains why the universe is so uniform on large scales. It ensures that every region of space expanded at an identical rate, leading to a cosmos where the laws of physics appear consistent everywhere we look. This uniformity extends even to the fundamental constants of nature, which have remained unchanged throughout the history of the universe. Inflation's effects are not confined to just its initial rapid expansion, but also influence how matter and energy distribute themselves over cosmic time. For example, the density of dark matter plays a crucial role in shaping galactic structures. As galaxies form and evolve, they trace back their origins to those minute quantum fluctuations set down by inflation. One might wonder what it means for us that we inhabit a universe stretched out from such an infinitesimal beginning. The vastness of space and the uniformity of its structure suggest a profound interconnectedness at cosmic scales, despite the immense distances separating galaxies. This realization can evoke a sense of both isolation and connection in our place within this expanding cosmos. The universe's expansion also implies that distant regions are becoming increasingly inaccessible. In billions of years, as space continues to stretch, signals from far-off galaxies will no longer reach us, creating isolated bubbles of observable reality. Yet, for now, we can study the remnants of inflation and its aftermath, learning about how the cosmos formed and evolved into the intricate web of stars, galaxies, and dark matter that makes up our universe. In summary, cosmic inflation not only explains the uniformity and vastness of the universe, but also provides insights into the nature of space, time, and the fundamental laws governing our existence. It remains one of the most intriguing concepts in cosmology, offering a glimpse into the origins of everything around us. In the vastness of space, a delicate imprint persists from the dawn of time, the cosmic microwave background radiation. This relic of the Big Bang bathes every corner of the observable universe with an average temperature of just 2.725 Kelvin, colder than even the most frigid reaches within our own galaxy. These microwaves have been traveling for nearly 13.8 billion years, carrying information from a time when the cosmos was only 380,000 years old. Each photon of this radiation has an origin story that began at almost the same moment in cosmic history. They trace back to a period known as recombination, when protons and electrons combined into neutral hydrogen atoms, allowing light to travel freely through space for the first time. This event marked the end of the cosmic dark ages, setting the stage for star formation and galaxy evolution. The uniformity across the sky is remarkable, with variations in temperature on the order of microkelvins, tiny fluctuations that hold clues about the early universe's structure. The cosmic microwave background provides an invaluable tool for cosmologists seeking to understand not only how the universe began, but also how it will end. By mapping these faint signals with exquisite precision, researchers can test theories about inflation, the rapid expansion of space shortly after the Big Bang, and other fundamental aspects of our cosmos. Inflationary models suggest that this period lasted less than 1/1,000,000th of a second, but had profound implications for the structure we see today. Each photon carries within it a piece of the story of how galaxies were born and grew, shaping the cosmic landscape we observe today. This radiation is not just an echo from the past. It also serves as a guide for exploring the future of our universe. As stars burn out and galaxies merge, these microwaves will continue to inform us about the evolving nature of space itself. The uniformity of the cosmic microwave background, despite its minute variations, suggests a level of initial homogeneity in the early universe that challenges our understanding of how such consistency could arise from chaotic conditions. Scientists have mapped these variations with increasing detail, revealing patterns that match predictions from inflationary models. These maps provide evidence for rapid expansion shortly after the Big Bang, a period during which space itself stretched faster than light could travel. This phenomenon occurred in an incomprehensibly short span of time, less than 1/1,000,000th of a second, but had profound implications for the structure we see today. The uniformity across 13.8 billion light-years indicates that every point in the observable universe is connected through this radiation, suggesting a level of initial homogeneity that challenges our understanding of how such consistency could arise from chaotic conditions. This unexpected insight into the early cosmos reveals that even slight variations in temperature can lead to the formation of galaxies and stars, hinting at the delicate balance between order and chaos. The cosmic microwave background also offers insights into phenomena beyond our galaxy's boundaries. By analyzing its polarization, researchers can study gravitational waves and other cosmic events that have left subtle imprints on this ancient radiation. These findings help us better understand not just the origins, but also the ongoing evolution of our universe. As we observe this radiation, we are witnessing one of the most ancient processes in the cosmos, a relic of the universe's infancy that continues to shape our understanding of its vastness and complexity. At the edge of a supermassive black hole's event horizon, space-time stretches and twists in ways that defy human comprehension. Here, time slows to a crawl for nearby objects, and light is stretched into longer wavelengths due to gravitational redshift. This boundary marks where our understanding of physics begins to falter. The temperature near this point approaches absolute zero, yet it's not due to a lack of energy, but because particles lack sufficient motion to interact. The event horizon also influences the behavior of nearby stars and galaxies through tidal forces. As objects approach the black hole, these forces stretch them along one axis while compressing them perpendicular to that direction, a process known as spaghettification. This phenomenon is akin to pulling apart taffy, where stretching and thinning occur simultaneously in opposite directions. For distant observers, this effect can manifest as bright flares or sudden changes in the luminosity of nearby stars. Despite being invisible to direct observation, event horizons leave imprints on their surroundings that can be studied indirectly. Gravitational lensing caused by massive objects warps light paths in predictable ways, allowing astronomers to map out unseen regions of space. This technique has revealed the presence of many black holes throughout our galaxy and beyond. The precision required for these measurements highlights the intricate nature of spacetime near such boundaries. The event horizon's role as an information boundary poses questions about the nature of reality and consciousness. If information truly cannot escape once inside, what does this imply for observers outside? This paradox challenges our understanding of causality and perception. It's reminiscent of philosophical conundrums where hidden truths remain concealed from direct observation, yet influence outcomes in profound ways. At this boundary, spacetime undergoes extreme distortions, creating conditions unlike anything found elsewhere in the cosmos. Particles near the event horizon move at speeds close to that of light, yet their paths are so twisted by gravity that they trace out complex orbits instead of straightforward trajectories. These intricate patterns echo the delicate dance of molecules in a gas cloud or the swirling motion of water down a drain. The temperature near an event horizon approaches absolute zero due to Hawking radiation, with temperatures reaching within 10 Kelvin of absolute zero. This process involves pairs of virtual particles being created just outside the boundary, where one particle escapes into space while its counterpart falls into the black hole, reducing the mass of the singularity over unimaginably long periods. The study of event horizons challenges long-held assumptions about the universe's structure and behavior. These boundaries push the limits of what we understand, prompting scientists to explore new theories that bridge general relativity with quantum mechanics. By examining phenomena at these extremes, researchers hope to unlock deeper truths about the nature of reality itself. The quest for understanding continues as astronomers peer ever closer into the heart of these cosmic enigmas. The event horizon's influence extends beyond its immediate vicinity, affecting the dynamics of galaxies and even shaping large-scale structures in the universe. The gravitational pull near a black hole can warp spacetime so dramatically that it influences the paths of distant stars and galaxies. This effect allows astronomers to infer the presence of massive objects like black holes from their distortions on light paths, but also reveals unexpected phenomena such as time dilation at extreme distances. Understanding event horizons also provides insights into the nature of time itself. Near these boundaries, time dilates significantly due to extreme gravitational forces, making it seem as though events occur more slowly for an observer near a black hole compared to one far away. This temporal distortion is a key aspect of Einstein's theory of general relativity and highlights how spacetime can be stretched or compressed depending on the presence of mass. The quest to understand event horizons continues with new technologies and theoretical models that push the boundaries of our knowledge. As scientists delve deeper into these cosmic mysteries, they uncover not only about black holes, but also fundamental aspects of physics and cosmology. Each discovery brings us closer to unraveling the enigmatic nature of space-time and the universe's most extreme environments. Amidst the cold and vast expanses of space, nebulae serve as cosmic forges where the elements crucial to life are born. These interstellar clouds contain not just hydrogen, but also traces of heavier elements like carbon, nitrogen, and oxygen, elements that were once part of long-dead stars. When a star reaches the end of its life, it explodes in a supernova, dispersing these elements throughout space. Over time, these materials coalesce into new stars and planets, carrying with them the seeds of future life forms. Each nebula plays a unique role in this grand process, acting as both a nursery for new stars and a laboratory where complex molecules are created. These molecules are carried through space by cosmic winds, seeding future star systems with the ingredients needed for life. The intricate balance between these forces ensures that our universe remains a dynamic place full of potential. This continuous cycle has been ongoing since long before our own sun formed, ensuring that new worlds may one day host life forms similar or different from our own. In certain nebulae, such as the Carina Nebula, stellar nurseries can span thousands of light years and contain enough material to form hundreds of thousands of stars. These vast clouds are not just passive regions in space. They are active participants in the grand process of cosmic evolution. They provide a glimpse into the future of our own galaxy, where similar processes will continue to shape new worlds. The recycling of heavy elements through supernovae explosions enriches future nebulae with complex materials essential for life. As massive stars end their lives in violent eruptions, they eject material enriched with heavy elements like iron and silicon into space. This ejected matter then becomes part of new nebulae, contributing to the increasing complexity of subsequent star systems. The cycle of stellar birth and death ensures that each generation of stars contains an ever more complex mix of materials, essential for the development of planets capable of supporting life. In some regions of space, temperatures can drop as low as 0.1 Kelvin near the center of certain nebulae, approaching absolute zero. This cold environment slows atomic motion almost to a halt, creating conditions where matter behaves in unexpected ways. These extreme temperatures are not found naturally anywhere on Earth and provide unique insights into quantum mechanics and particle behavior under such conditions. Understanding how these elements travel through space gives us insight into the interconnectedness of all celestial bodies. The iron in your blood was forged in stars that died before our sun existed. This is one example of how cosmic events have shaped life on Earth and possibly elsewhere. As we observe these distant nebulae, we are not just watching star formation. We're witnessing a process that has given rise to the elements necessary for all known forms of life. The processes within these stellar nurseries are finely tuned, governed by forces both familiar and alien to us. Gravity pulls together clouds of gas and dust, while magnetic fields and radiation push back, creating a delicate balance that can take millions of years to unfold. In this cosmic dance, the smallest changes in temperature or density can lead to vastly different outcomes. Some regions will collapse into stars, others may form planets, and some might remain as diffuse clouds for eons. This variability underscores the unpredictable nature of star formation, where chance plays a significant role alongside predictable physical laws. Consider that within these nebulae, new elements are being forged continuously. Every supernova explosion adds to this elemental inventory, enriching the interstellar medium with heavier atoms. These newly created elements can take millions of years to spread throughout the galaxy, gradually becoming part of future stars and planets. This slow diffusion means that each generation of stars is more chemically complex than the last, a trend that has been ongoing since the universe's earliest epochs. It is this gradual enrichment that allows for the eventual formation of planets with atmospheres rich in oxygen, nitrogen, and other elements necessary for life as we know it. Moreover, these nebulae are not isolated phenomena. They are part of larger galactic structures. In our own Milky Way, stellar nurseries often cluster together, forming regions of intense star formation known as giant molecular clouds. These clouds can stretch across hundreds of light years and contain enough material to form thousands of stars. The sheer scale of these formations is staggering when compared to the average distance between stars in our galaxy, which is typically several parsecs apart. This clustering of stellar birthplaces suggests that regions favorable for star formation are not randomly distributed, but instead occur in specific areas where conditions align perfectly. The materials expelled by supernovae do not only enrich future nebulae, they also influence the evolution of galaxies as a whole. As these elements spread throughout space, they can. The moment when the first stars ignited and light spread through the previously dark cosmos marks a profound transition in the universe's history. This initial glow, known as the cosmic dawn, occurred approximately 100 to 200 million years after the Big Bang. The light from these nascent stars began its journey across the void, illuminating an environment that had been shrouded in darkness since the birth of the cosmos. As photons from these early stars traversed space, they encountered a universe vastly different from our own. At this time, the universe was much smaller and denser, with matter distributed unevenly. This uneven distribution led to regions where gravity could pull together gas clouds, eventually forming the first stars. These stars were massive and short-lived compared to their modern counterparts, burning through their fuel at an extraordinary rate. The light from these early stars not only illuminated their immediate surroundings, but also began to interact with the cosmic microwave background radiation, a remnant of the Big Bang that fills every corner of the observable universe today. This interaction altered the temperature distribution of this ancient radiation, providing a subtle signature for astronomers to detect and study. The imprint left by the first stars on this radiation is faint but unmistakable, offering clues about the conditions in which these luminous bodies formed. These early photons also played a crucial role in reionizing hydrogen atoms scattered throughout space. Before the cosmic dawn, most of the universe's hydrogen was ionized, meaning its electrons and protons were separated. The intense radiation from the first stars recombined some of this hydrogen, marking a significant step toward the transparent universe we observe today. This process took millions of years to complete, gradually clearing the fog that had enveloped the cosmos. The journey of these ancient photons through space is marked by their interaction with cosmic structures like galaxies and galaxy clusters. As they pass near massive objects, gravitational lensing can bend their paths, creating arcs or multiple images in telescopic observations. This phenomenon not only distorts our view, but also provides valuable information about the distribution of mass in the universe. The light from these early stars has traveled for billions of years, crossing vast distances to reach us. Each photon from those first stars carries with it a precise measurement of 100 to 200 million years since the Big Bang, tracing back to an era when the universe was young and full of potential. These particles have been traveling through space for so long that they have experienced time differently than we do on Earth. Their journey is a testament to the vastness of the cosmos and the enduring nature of light itself. This ancient light continues to inform our understanding of how galaxies, stars, and even life itself came to be in this intricate cosmic web. The photons from those first stars eventually reached regions where they encountered clouds of molecular hydrogen, the raw material for future star formation. These clouds are vast, often spanning hundreds of light years, and contain the ingredients necessary for stellar birth. As the ancient light interacted with these dense pockets of gas, it triggered a cascade of events that would lead to the creation of new stars across the cosmos. In some cases, these photons also influence the structure of galaxies themselves. By heating and ionizing nearby gas clouds, they helped sculpt the intricate patterns that define galactic architecture. This process is part of what astronomers call cosmic feedback, where energy from stars affects their environment in complex ways. The light from those first stars not only illuminated the universe, but also shaped its future by influencing how galaxies grow and evolve. The journey of these photons through space is a remarkable testament to the interconnectedness of cosmic phenomena. Each photon carries with it the legacy of the universe's earliest moments, traveling across billions of years to reach our telescopes. As we observe this ancient light, we are witnessing not just distant stars, but also the very processes that gave rise to galaxies, planets, and potentially life itself. This enduring illumination serves as a reminder of the vast timescales over which cosmic events unfold, and the intricate web of cause and effect that governs the universe's evolution. Consider a grain of sand nestled in your palm, weighing little more than a fraction of an ounce. Now imagine expanding that single grain to encompass the entire volume of our solar system, including every planet and their moons. This hypothetical supersand would still be less dense than water, floating effortlessly if submerged in space's near vacuum. Yet, this minuscule object exists within a cosmos so vast it defies comprehension, stretching across billions upon billions of light years. To grasp the sheer enormity, let us compare our solar system to the galactic scale. The Sun orbits the center of the Milky Way once every 240 million years, traversing an immense distance in this cosmic cycle. Yet, despite this staggering journey, it remains a mere speck when compared to the vastness beyond our galaxy. Andromeda, approaching at 110 kilometers per second for a future collision with the Milky Way, is but one of countless galaxies floating within the observable universe. Imagine standing on the surface of Earth and gazing up at the night sky. The stars you see are distant suns, each potentially surrounded by their own planetary systems. Now envision those stars not as points of light, but as bustling spheres filled with complex processes like fusion reactions and gravitational dances. Even in our galaxy's spiral arms, these stellar bodies are spaced so widely that the nearest star to our Sun is over 4 light-years away, more than 25 trillion miles. Consider the temperature at the center of a red giant star compared to the chill of interstellar space. In the core of such a massive celestial body, temperatures can reach tens of millions of degrees Celsius, where atomic nuclei fuse in an unceasing dance that sustains its brilliance for millennia. Conversely, far from these stellar furnaces, deep space averages just 2.725 Kelvin, only a few decimal points above absolute zero, colder than even the coldest known places on Earth like Antarctica's high plateaus. Astronomers have discovered exoplanets with surface temperatures reaching up to 2,760 degrees Celsius due to their proximity to their parent stars. These extreme conditions contrast sharply with the frigid vastness between these celestial bodies, where matter exists in sparse clouds of gas and dust particles. This interstellar environment is so empty that a cubic meter of space might contain only one hydrogen atom, creating a paradoxical scenario of both incredible density within stellar cores and extraordinary emptiness elsewhere. Within this cosmic framework, the life cycle of stars plays out over incomprehensible timescales. A single star's birth from a collapsing cloud of gas can take millions of years, while its death in a supernova explosion lasts mere seconds. This vast difference in duration underscores the transient nature of even the most enduring celestial phenomena. The remnants of these explosions, like neutron stars and black holes, continue to influence their surroundings long after the original star has faded. As you reflect on this scale, it is worth noting how such vastness impacts the fundamental constants governing physics in different parts of space. For instance, near a black hole's event horizon, gravity distorts time so severely that clocks would tick at rates significantly slower compared to those farther away. This phenomenon underscores not only the enormity, but also the variability inherent within the cosmos, challenging our understanding of uniformity across its expanse. The universe is estimated to be about 13.8 billion years old, according to current cosmological models. During this time, countless stars have been born and died, contributing to the cosmic microwave background radiation that permeates every corner of the observable universe. This radiation, a remnant from the Big Bang, has an average temperature of about 2.725 Kelvin, colder than even the most frigid reaches within our own galaxy. Standing on a neutron star's surface is an unimaginable experience, where gravity distorts your body infinitely thin. At this extreme, every atom in your body would be compressed to unprecedented levels, each layer of tissue crushed into molecular flatness within milliseconds. The gravitational force presses down with a weight of over 1 billion metric tons per square centimeter, bending space and time beyond our comprehension. Surface temperatures on these stars can reach up to 2 million degrees Celsius, incinerating anything that dares to approach. To put this into perspective, if you were to stand here, your body would be flattened thinner than the thickness of a sheet of paper in an instant. Yet paradoxically, this extreme pressure stabilizes the star's core, preventing it from collapsing further into a black hole. The matter within is packed so densely that each cubic centimeter contains more mass than any material on Earth could ever achieve. This density is such that even light struggles to escape the surface, bending as it fights against the immense gravitational pull. Neutron stars are remnants of ancient supernovae, their existence marking the violent deaths of massive stars long since gone. From our vantage point on Earth, billions of light years away, the effects of this intense gravity are evident in the redshift and dimming of photons emitted from these stellar corpses. This cosmic stretching of light not only reveals the star's density, but also provides a window into the warping of spacetime itself. The universe is estimated to contain thousands of neutron stars, each one a relic of past astronomical events. These remnants scatter elements across space as they cool and age, contributing to the recycling of cosmic materials. The iron in your blood likely originated from such a supernova explosion that occurred long before our sun was born. This interstellar mixing ensures that every element heavier than hydrogen is forged in these fiery deaths, setting the stage for future generations of stars. As you stand on this unimaginably dense surface, every particle in your body would be subjected to forces so extreme they challenge the very limits of known physics. The stability of a neutron star hinges on quantum effects that lock neutrons into an incredibly dense lattice structure, preventing further collapse despite gravity's relentless pull. This balance between gravitational force and nuclear strength offers a profound glimpse into the extraordinary conditions that govern the cosmos. Each neutron star represents not just a point in space, but also a testament to the cyclical nature of stellar life. Incredibly, neutron stars are among the densest objects known in the universe, with densities exceeding those found even in atomic nuclei. A single teaspoon of neutron star material would weigh as much as Mount Everest on Earth. This extreme density is achieved through the quantum degeneracy pressure of neutrons, which resists further compression. Yet, despite this resistance, the gravitational pull remains so intense that it warps spacetime around the star, creating a region known as its event horizon if it were to collapse into a black hole. The surface of a neutron star is not static. It is constantly bombarded by cosmic rays and high-energy particles from nearby supernova remnants. These interactions can cause localized heating and cooling events on the star's crust, leading to complex patterns of temperature variation across its surface. This dynamic environment contrasts sharply with the relative calm of deep space, where temperatures approach absolute zero in regions far removed from stellar activity. The contrast between these extremes highlights the vast range of conditions that exist within our universe. In a billion years, some neutron stars will have cooled sufficiently to become stable and no longer emit detectable radiation. These objects, known as isolated neutron stars or black widows, will drift silently through space, their magnetic fields gradually decaying over time. Meanwhile, others may merge with binary companions in spectacular collisions that release bursts of gravitational waves and gamma rays. The life cycle of a neutron star is thus both brief and eventful, spanning from the cataclysmic supernova explosion to eventual quietude or violent demise. The universe contains an estimated 10 million neutron stars within our galaxy alone, each one a unique remnant of stellar evolution. These objects are not only fascinating in their own right, but also serve as laboratories for testing theories about extreme physics and cosmology. By studying them, scientists gain insights into the fundamental forces that govern matter under conditions far beyond what can be replicated on Earth. The study of neutron stars thus bridges the gap between human curiosity and the cosmic scale, offering a window into the universe's most enigmatic phenomena. Quantum jitters at the smallest scales might influence the largest structures in the universe through a process known as quantum fluctuations. These minute variations occur everywhere, even within the heart of stars where nuclear fusion takes place. The internal pressure from these processes counteracts gravity, preventing the star from collapsing. This delicate balance ensures that stars can shine for billions of years, producing heavy elements essential for life. These elements are eventually dispersed into space when a star dies, enriching interstellar clouds with the ingredients needed to form new generations of stars and planets. At the subatomic level, quantum fluctuations occur continuously, even in regions as vast as deep space. In these environments, where temperatures approach absolute zero, atomic motion essentially stops because particles lack sufficient energy to move. However, at such extreme conditions, quantum mechanics predicts that tiny fluctuations can still arise, leading to brief appearances of particle-antiparticle pairs before they annihilate each other. These fleeting events are significant in the context of cosmic inflation, a period when space-time expanded exponentially just after the Big Bang. This rapid expansion smoothed out irregularities, laying the groundwork for the large-scale structures we observe today: galaxies, galaxy clusters, and vast voids between them. The influence of quantum fluctuations extends beyond stellar interiors to the cosmic microwave background radiation. This leftover heat from the Big Bang fills every corner of the observable universe with an average temperature of 2.725 Kelvin. These minute thermal variations are incredibly subtle, but crucial for cosmologists studying how galaxies form and evolve. The slight differences in density caused by quantum fluctuations lead to regions where matter accumulates, eventually becoming the seeds for galaxy formation. Interestingly, these initial perturbations set the stage for the intricate cosmic web we observe today. In some extreme environments, such as near black holes or within neutron stars, these quantum jitters can become particularly significant. Here, the forces of gravity are so intense that they warp space-time itself, causing time and space to behave in ways unimagined by classical physics. In these regions, particles experience immense gravitational tides, further emphasizing how the smallest scales profoundly affect the largest cosmic phenomena. This interplay between quantum mechanics and general relativity is crucial for understanding some of the most extreme environments in our universe. The implications are profound. If quantum fluctuations at the subatomic level influence the structure of entire galaxies, then every particle in our universe holds within it the potential for cosmic significance. For instance, the iron in your blood was forged in a star that died before our sun existed. This realization invites us to consider how such minute variations might have shaped not just the structures we see now, but also the conditions necessary for life itself, including the elements that form the building blocks of organic molecules. The universe's expansion began as an inflationary phase driven by these quantum fluctuations. In less than 1/1,000,000,000 of a second after the Big Bang, space-time expanded exponentially, smoothing out irregularities that would have otherwise resulted in clumpy or uneven distributions of matter. This rapid expansion laid the groundwork for the large-scale structures we observe today: galaxies, galaxy clusters, and vast voids between them. Without this initial quantum-driven inflation, the universe might have been too chaotic to support life as we know it. In deep space, the temperature hovers at a mere 27.25 Kelvin, colder than any naturally occurring place on Earth. Yet, this is not the coldest that our universe will reach. As stars exhaust their nuclear fuel and die out, vast stretches of intergalactic space will become even chillier, approaching absolute zero. Imagine a future where galaxies no longer hold together due to gravity, but instead drift apart in an endless dance of isolation. Each galaxy, once a bustling city of stars, will exist alone on its cold journey through time. The Milky Way and Andromeda, now merged into one larger structure, will continue to separate from other systems, each more isolated than the last. This dispersion is not driven by expansion, but by the natural cooling and dimming of all stellar light. Black holes, with their immense gravity and mass, will also play a significant role in this cold universe. Over an incomprehensible length of time, far longer than the age of our current universe, they will evaporate through Hawking radiation. This slow process ensures that even small black holes would take more than 1067 years to vanish completely. In contrast, supermassive black holes with millions or billions of solar masses might persist for trillions upon trillions of years. The remnants of stars will contribute further to the cooling cosmos as well. White dwarfs and neutron stars, born from stellar explosions or collapses, will slowly radiate away their heat over eons. These dead stars will eventually be colder than the space around them, effectively becoming dark, inert points in the vast void. As they cool down, the faintest light from distant galaxies will dim, lost in the pervasive darkness. In 1 billion years, the temperature difference between space and these cooling cosmic objects will diminish to less than 1 Kelvin, making it nearly impossible to distinguish one from another. The universe, once teeming with light and life, will become a uniform sea of near-absolute zero temperatures, where even the faintest glow is swallowed by the encroaching darkness. This future prompts an intriguing question. How would this cold, dark cosmos affect the perception of time? In such a state, where nothing significantly changes or moves, time itself might become almost meaningless. As stars fade and black holes evaporate, the universe will reach a point where it is nearly devoid of any significant energy output. This era, known as the heat death of the universe, marks the end of all possible thermodynamic processes. In this state, even the faintest cosmic microwave background radiation will have dissipated into nothingness, leaving only an eerie silence and darkness that stretches across every corner of existence. The remaining particles will drift aimlessly, their interactions so rare as to be practically non-existent. However, in this final stage, some scientists speculate that quantum fluctuations might create fleeting pockets of energy, offering a brief reprieve from the uniformity of absolute zero. In deep space, the temperature hovers at a mere 27.25 Kelvin, colder than any naturally occurring place on Earth. Yet, this is not the coldest that our universe will reach. As stars exhaust their nuclear fuel and die out, vast stretches of intergalactic space will become even chillier, approaching absolute zero. Imagine a future where galaxies no longer hold together due to gravity, but instead drift apart in an endless dance of isolation. Each galaxy, once a bustling city of stars, will exist alone on its cold journey through time. The Milky Way and Andromeda, now merged into one larger structure, will continue to separate from other systems, each more isolated than the last. This dispersion is not driven by expansion, but by the natural cooling and dimming of all stellar light. Black holes, with their immense gravity and mass, will also play a significant role in this cold universe. Over an incomprehensible length of time, far longer than the age of our current universe, they will evaporate through Hawking radiation. This slow process ensures that even small black holes would take more than 1067 years to vanish completely. In contrast, supermassive black holes with millions or billions of solar masses might persist for trillions upon trillions of years. The remnants of stars will contribute further to the cooling cosmos as well. White dwarfs and neutron stars, born from stellar explosions or collapses, will slowly radiate away their heat over eons. These dead stars will eventually be colder than the space around them, effectively becoming dark, inert points in the vast void. As they cool down, the faintest light from distant galaxies will dim, lost in the pervasive darkness. In a billion years, the temperature difference between space and these cooling cosmic objects will diminish to less than 1 Kelvin, making it nearly impossible to distinguish one from another. The universe, once teeming with light and life, will become a uniform sea of near-absolute zero temperatures, where even the faintest glow is swallowed by the encroaching darkness. This future prompts an intriguing question. How would this cold, dark cosmos affect the perception of time? In such a state, where nothing significantly changes or moves, time itself might become almost meaningless. As stars fade and black holes evaporate, the universe will reach a point where it is nearly devoid of any significant energy output. This era, known as the heat death of the universe, marks the end of all possible thermodynamic processes. In this state, even the faintest cosmic microwave background radiation will have dissipated into nothingness, leaving only an eerie silence and darkness that stretches across every corner of existence. The remaining particles will drift aimlessly, their interactions so rare as to be practically non-existent. However, in this final stage, some scientists speculate that quantum fluctuations might create fleeting pockets of energy, offering a brief reprieve from the uniformity of absolute zero. The radiation from quasar J1342 plus 928 travels at nearly the speed of light, spanning vast distances before reaching Earth. This journey spans tens of millions of years, underscoring the immense scale and age of the universe. Each photon arriving here carries information about conditions 670 million years ago, illuminating an era when galaxies were still in their infancy. The quasar's neighbor galaxy is a relic from this early epoch, with its young stars forming under vastly different conditions than those found in more mature galaxies like our own Milky Way. These stars are born within clouds of molecular hydrogen that can span up to hundreds of light years, providing the raw material for stellar birth and eventual death. This process highlights how quasars, powered by supermassive black holes, influence their surroundings on profound scales. The intense radiation from J1342 plus 928 strips atoms from nearby interstellar clouds, ionizing the surrounding regions and altering their ability to form new stars. This interaction demonstrates the complex relationship between active galactic nuclei and their host galaxies, shaping the distribution of matter and energy throughout the cosmos. The quasar's radiation can also heat up these clouds, causing them to expand or disperse, further influencing star formation in its vicinity. In contrast to the cold temperatures found elsewhere in space, averaging around 2.725 Kelvin, the region near a supermassive black hole like that powering J1342 plus 928 experiences extreme heat due to accretion processes. This heat can reach millions of degrees Celsius, far exceeding even the hottest known exoplanet temperatures. Yet, despite this intense radiation, nothing can escape once it crosses the event horizon, a boundary beyond which not even light can travel. The quasar's neighbor galaxy provides a unique snapshot of cosmic evolution at its earliest moments. Its stars are formed from gas enriched with elements heavier than hydrogen and helium, which were forged in earlier generations of stars that have since died out. This recycling process is crucial for the formation of planets like Earth, where life as we know it depends on these heavy elements. The light emitted by J1342 plus 928 reaches us after a journey spanning nearly 670 million years, offering insights into the conditions that prevailed during the early stages of galaxy formation. By analyzing this ancient light, scientists can refine their models of how galaxies grow and evolve over billions of years, providing deeper understanding of cosmic processes that have shaped our universe. The quasar's glow is a testament to the immense energy released by supermassive black holes as they consume surrounding matter. This process, known as accretion, involves material spiraling into the black hole and heating up due to friction, creating intense radiation that can outshine entire galaxies. The gravitational forces at play near such an object are so powerful that they warp space-time itself, bending light paths and affecting nearby objects in ways that challenge our understanding of physics. Despite being billions of years old, this quasar remains one of the brightest known objects in the universe, a beacon from the dawn of cosmic time. The neighboring galaxy to J1342 plus 928 is a critical piece of evidence for theories about how galaxies grow and interact. It shows us that even at such early times, galaxies were already engaged in complex interactions, with quasars playing a pivotal role in shaping their environments. The presence of this quasar suggests an active period of star formation and black hole growth, processes that are still ongoing today, but on a much smaller scale within our own galaxy. This observation helps astronomers piece together the timeline of cosmic events, revealing how galaxies evolved from simple structures into the intricate systems we see today. The radiation emitted by J1342 plus 928 not only illuminates its immediate surroundings, but also provides valuable data for studying distant regions of space. By analyzing the light spectrum, scientists can determine the composition and temperature of the gas surrounding the quasar, offering clues about the conditions in which stars form and evolve. This information is crucial for understanding how galaxies like our own have developed over time, from their earliest stages to the present day. The discovery of such distant quasars challenges previous assumptions about the rapidity with which galaxies could grow after the Big Bang. These objects suggest that supermassive black holes formed very early in cosmic history, potentially through a series of mergers and accretion events that occurred within just. Cosmic rays from distant reaches of space bombard Earth's atmosphere, initiating a cascade of secondary particles detectable on the ground. These high-energy protons and atomic nuclei interact with air molecules at altitudes above 10 kilometers, producing pions and muons that decay into neutrinos and gamma rays. This process creates a shower front moving downward through denser layers of atmosphere at nearly the speed of light. By the time it reaches sea level, millions of secondary particles have been generated from just one primary cosmic ray. Each collision within this cascade releases energy equivalent to the kinetic force of a speeding bullet, yet these interactions occur silently and unseen. The sheer number of particles involved is staggering. For every single cosmic ray that enters our atmosphere, thousands more are produced in its wake. This phenomenon underscores the scale at which natural processes operate far beyond human-engineered experiments like particle accelerators on Earth. At ground level, specialized detectors capture traces of these showers, providing scientists with invaluable data about cosmic rays and their origins. These instruments can measure the arrival time and energy distribution of secondary particles, offering insights into how cosmic rays travel through space and interact with our planet's magnetic field. This information helps refine models predicting solar activity and radiation exposure risks for astronauts. The interaction between cosmic rays and Earth's atmosphere is not uniform. It varies depending on altitude, atmospheric density, and the angle at which incoming particles approach. Higher energy cosmic rays tend to penetrate deeper into the atmosphere before their energy is fully dissipated, while lower energy ones are absorbed more quickly near the surface. This variability introduces complexity in understanding how these particles contribute to phenomena such as cloud formation or even climate change. Moreover, cosmic ray showers can also occur at higher latitudes, where Earth's magnetic field funnels charged particles towards the poles. These regions, known as auroral zones, experience an increased frequency of cosmic ray interactions. The resulting light displays, auroras, are a visible manifestation of this interaction between space and atmosphere. However, these lights are not solely caused by cosmic rays, but also involve solar wind particles interacting with Earth's magnetic field. Ground-based observatories track the trajectories of secondary particles produced in cosmic ray showers, revealing patterns that help scientists understand how these energetic events unfold over time. This data provides a unique glimpse into the dynamic processes occurring within our atmosphere and beyond. While cosmic ray showers are detectable on the ground, they also leave an imprint in the upper layers of Earth's ionosphere, where charged particles can alter radio wave propagation. The energy released in each cosmic ray collision is immense, often exceeding the capabilities of any man-made particle accelerator. For instance, a single high-energy proton from space might possess more kinetic energy than the entire Large Hadron Collider at CERN. This vast discrepancy highlights the scale and power of natural cosmic phenomena compared to human-engineered experiments. Particles produced in these collisions include not only pions and muons, but also electrons and positrons. These secondary particles can ionize air molecules, leading to the formation of ions that play a role in cloud nucleation. The connection between cosmic rays and cloud formation remains an area of active research, with implications for understanding climate dynamics on Earth. Cosmic ray showers offer a unique window into the universe's history, as they carry information about distant events such as supernovae or galactic collisions. Some of these particles have traveled across billions of light years before reaching our atmosphere, carrying with them the remnants of ancient stellar explosions. By studying their composition and energy levels, scientists can trace back to the conditions under which these cosmic rays were born. In addition, cosmic ray showers provide insights into the structure of space itself. The paths that these particles take through interstellar space are influenced by magnetic fields and other cosmic phenomena, offering clues about the distribution of matter in our galaxy. This information helps refine models of galactic dynamics and the large-scale structure of the universe. The journey of a single cosmic ray from its source to Earth's atmosphere involves crossing an average distance of 100,000 light-years, navigating through interstellar clouds and magnetic fields that can bend or scatter its path. Despite these challenges, some particles manage to reach our planet, providing us with a glimpse into the farthest reaches of the cosmos. Once inside Earth's atmosphere, cosmic rays undergo a series of transformations, producing secondary particles in their wake. This process is akin to a chain reaction, where each collision spawns new particles that continue the cycle until all energy is dissipated. The resulting shower can extend over several kilometers on Earth's surface, leaving behind traces detectable by specialized instruments. Despite the relentless march towards darkness, every dying star broadcasts light brighter than its birth. In vast molecular clouds, temperatures can plummet to -270 degrees Celsius, mere fractions above absolute zero. These regions of space are cooler than others despite being surrounded by hot plasma. The contrast between the coldness within these clouds and the surrounding heated environment is akin to a freezer in an oven. This temperature disparity allows for unique chemical reactions that would otherwise be impossible at higher temperatures. Within these molecular clouds, complex molecules like water ice and carbon monoxide form, serving as building blocks for future stars and planets. These clouds span hundreds of light years, containing enough material to form thousands upon thousands of suns. As the clouds collapse under their own gravity, they spin faster, much like an ice skater pulling in her arms. This rotation can lead to the formation of protoplanetary disks around young stars, where planets may eventually coalesce. The process of cooling within these molecular clouds is not passive but active, driven by the interplay between radiation and molecular collisions. As particles lose energy through these collisions, they cool further, approaching absolute zero, a point at which atomic motion essentially stops because particles lack sufficient energy to move. This state of near-zero temperature allows for the formation of complex molecules that are essential for life as we know it. In some regions of space, temperatures drop so low that even the coldest places on Earth seem warm in comparison. These cold spots can be found within vast molecular clouds, where the density of particles is high enough to facilitate cooling through collisions, but sparse enough to allow radiation to escape freely. This unique balance between density and transparency enables these regions to become some of the coldest known in the universe. The universe's extreme temperature contrasts serve as a reminder of its dynamic nature. While stars burn brightly, their eventual deaths lead to cooler environments that foster new beginnings. These cool regions amid hot plasma defy intuition, but are essential for the ongoing cycle of cosmic creation and destruction. As these clouds continue to collapse and form new stars, they ensure that the cosmos remains a place where life's building blocks can emerge from the coldest depths of space. In these cold molecular clouds, the temperature gradient plays a crucial role in shaping the universe's future. The outer layers of these clouds are warmer than their interiors due to the absorption and re-emission of radiation from nearby stars. This difference in temperature drives convection currents within the cloud, stirring up its contents like a cosmic cauldron. These movements help mix the raw materials necessary for star formation, ensuring that the elements forged in earlier generations of stars are distributed evenly. The cooling process is not uniform across all regions. It varies depending on factors such as density and proximity to other celestial bodies. In some areas, the temperature can drop so low that molecules begin to stick together, forming larger structures like dust grains or even simple organic compounds. This intricate dance of particles, driven by the delicate balance between cooling and heating, sets the stage for the eventual birth of new stars and planets. These molecular clouds are not just passive repositories of cold gas. They are dynamic environments where complex chemistry unfolds. The formation of molecules in these frigid regions is a testament to the resilience of matter under extreme conditions. It is here that hydrogen atoms combine with other elements, creating the building blocks for future solar systems. Each molecule formed represents a step toward the creation of new life-supporting planets. As we observe these cool regions from Earth, They appear as dark patches against the backdrop of starlight. Yet, within them lies the potential for countless new beginnings. The paradox of finding such cold spots amidst the vast sea of hot plasma underscores the complexity and beauty of our universe. These regions remind us that even in environments where conditions seem inhospitable to life, there is always a possibility for something extraordinary to emerge. In the vastness of space, each dying star lights up one last time, brighter than its birth, before fading into the cosmic dark. The journey through the cosmos now comes to a quiet end. Thank you for exploring the stars with us tonight. If you enjoyed this peaceful voyage, do consider subscribing and leaving a like. Good night, Chinese letter, 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 Chinese letter.